Let us start this lecture. Let's start this lecture and we will talk about heat engines. A heat engine is a system that converts heat to mechanical work. A heat engine consists of three bodies. Two first bodies are very big. These bodies have almost infinitesimal, or almost infinite heat capacity, and their temperature do not change if they interact with smaller bodies. A big body, these bodies are heat reservoirs. One reservoir is hot. It is a reservoir whose temperature is high. And the other reservoir is cold. We can say sometimes it's said that this is a heater and this is a cooler. We will denote the temperature of hot reservoir by T2. The temperature of cold reservoir will be denoted by T sub 1. By construction, T2 is greater than T1. A certain gradient of the heat engine is a small system. The system changes its state periodically. It interacts with hot reservoir and cold reservoir and makes a work. And this small system is called working body. Finally, we have to assume that we have some kind of environment here, and working body will make work on the environment. Let me explain the general scheme of working of heat engine. At the first stage, working body interacts with hot reservoir and takes some quantity of heat, which I denote Q sub 1. Then it makes work. Let me denote the work A sub 1, this work. And then, after that, it interacts with cold reservoir. And it gives out the quantity of heat Q2. I take the absolute value of Q2 because Q sub 2 is negative. The heat goes from the working body and to cold reservoir. And finally, some environment makes some work on the working body, and this work is A2. This work, let me stress that these two stages, the heat flow from working body to cold reservoir and the work from environment are needed for only one purpose. They used to return working body to initial state. So as far as we have a cyclic process, working body follow one part of the process, and then we have to return it to the initial state. And here we need the work, and here we need heat, quantity of heat, Q sub 2. Let us find some restrictions on the quantities Q and A, that follow from the first law of thermodynamics and second law of thermodynamics. Let us denote by Q the total heat quantity that is obtained by the working body. As far as Q2 is negative, let me write it here. Q2 is negative. Okay, let me here. Maybe equal, and we will see that equal is not possible. Okay, so we can represent this formula is another way. U1 minus absolute value of Q2. The total work is equal to the work in stages 1 and 2. So we have A sub 1 plus A sub 2. This is the quantity of heat that is obtained by working body during the cyclic process, during the whole cycle, and this is a total work. Let us now apply a first law of thermodynamics to the working body. The change of internal energy equal to the sum to the amount of heat that is obtained by body minus work. We told that the change of the working body changes state in accordance with the cyclic process. So after a cycle, it returns to an initial state. So delta U equals to U1, U2 minus U1, and this is 0. Because U2 and U in final and initial state are equal. Final and initial state are equal. So we have an equality from here. From here, we have equality that Q equals A. The total amount of heat obtained by the working body is transferred into work. Okay, this is so-called principle of equivalence of heat and work. You can principle of equivalence of heat and work. Okay, and this equality gives us hope that we can convert all the heat into the work. This is not true, and this is not correct. There are several points, and the main one is that is that typically the hot reservoir takes its energy from the burning of fuel. Let me take some kind of candle here. It takes his energy from the burning of fuel. And here, cold reservoir usually is atmosphere. This means that the heat Q sub 2 that goes to the cold reservoir is not useful. While it's important how many heat is taken from hot reservoir. The efficiency of the heat engine, eta is a letter that is used for efficiency, is a ratio of the work produced by the engine to the quantity of heat obtained from hot reservoir, because this amount of heat determines how much fuel we need here. And we can represent this in equivalent form, Q1 minus absolute value. Okay, let me several equivalent forms here, and another equivalent form is here. Okay, not good. Okay, not problem. Q1. Okay, and here minus Q2. Absolute value of Q2 divided by Q sub 1. And we see the following. If Q sub 2 is greater than 0, the absolute value of Q sub 2 is greater than 0, then eta less than 1. This means that only part of heat energy, is transferred into the mechanical work. Thermodynamics prevents construction of two types of engines that violate this rule. And these engines are connected with the issue of perpetual motion. These engines are called perpetual engines. Perpetual engine. This is an imaginary type of engine that produces more work than it takes energy, from outside. And perpetual engine of first type, it's the engine that makes work without changing in the environment. So perpetual engine of first type, it's some engine that continuously makes work, but do not take energy from outside. Thermodynamics, the first law of thermodynamics tells us that this engine is not possible. Let us prove this fact. Let us apply the first law of thermodynamics to the perpetual engine. Here. Okay. here. And the working body changes its state periodically. So its internal energy after a cycle of work do not change. It do not take energy from outside. So the only option is A equals to 0. This means that this engine can't make work. We were wrong when we state that this engine can exist. And let us consider perpetual engine of second type. This is a system that transfers all the heat, that converts all the heat that is obtained from hot reservoir into the work. So this is a special engine for which Q1 equals to A. The existence of such engine is inconsistent with the second law of thermodynamics. This is not possible by second law of thermodynamics. I can tell very simple rule to remember what is happening. How to remember what's happening here. Okay. Perpetual, I say that first law of thermodynamics tells us that perpetual engine of first type is impossible. Second law of thermodynamics tells that perpetual engine of second type is impossible. Okay. Now we know what is impossible, but let us ask ourselves what is possible. And here, and our question is the following. Let me our question is the following. Assume that we take certain amount of heat, let's say Q, from our hot reservoir. What is the maximal work that can be produced from this part of heat? So in another question, what part of the heat can be produced? What work can be produced from the fixed amount of heat Q? This question is very non-trivial because the work is a function of process. We can go from initial state to final state by different ways, and these different ways will have different work. But can we estimate the maximal work if we know final state and initial state? In fact, we can. And here we will prove the statement that is called, let's say, maximum work theory. Maximum work theory. Let us assume that let us assume that our system, it could be a working body or some other system, goes from the state alpha to the state alpha prime. And in the process of changing of its state, it is in contact with heat reservoir with temperature TR, T sub R. Then the work produced by the system meets this inequality. And okay, here. And let us assume that delta S is the change of entropy of the system, and delta U is the change of internal energy of the system. Then the work produced by the system meets this inequality. TR, T sub R multiplied delta S minus delta U. The inequality becomes equality in reversible process. Reversible process. Equality. Only in reversible. Let us prove it. Let's consider a big system that includes our system and heat reservoir. This system is closed, so its entropy, so the system is closed, so the entropy of the big system cannot decrease. If delta SF is a change of entropy of heat reservoir in the process, then delta SR, S sub R plus delta S greater or equals than 0. And here equality has a place only in reversible process. We know that the entropy do not change in reversible process, while if the entropy increases, we have irreversible process. And now we can multiply the left and right hand side by T sub R. T is positive, so no problem. We have the same inequality. But now, with what we see? Q T sub R multiplied by delta sub R is the amount of heat that is obtained by the heat reservoir in the process. But we know that our system is closed, so all the heat that is obtained by our reservoir is taken from the system. So this is minus Q. So we have dr delta S minus Q is greater than 0. And this is a consequence of the first and the second law of thermodynamics. Now we can apply the first law of thermodynamics to the system. delta U equals Q minus A. From here, we find Q equals to delta U plus A. And we substitute this expression here. So we get TR delta S minus Q. No, not the minus. Minus delta U minus A greater than 0. Now we distribute all the terms to the left and right hand side of inequality. We get what we want. TR multiplied by delta S minus delta U. And let me again, equality is only in reversible process. And if the process is reversible, we make the maximal work, A maximum, equals to TR delta S minus delta U. And this is the maximal work. And this is the maximal work that can be produced in the process in which the entropy and internal energy of the system changed by delta S and delta U. Okay. And now, okay, so we have proved this very general statement, and let us apply this to the heat engines. Let us divide our heat engine into two subsystems. Okay. The first subsystem will include hot reservoir and all the environment, working body, and cold reservoir will be the second subsystem. Okay, let's second subsystem. And let us and let us apply the second subsystem. So we have, as hot reservoir is the reservoir, we have TR equals to T2. And let us compute that, and now we have to find the change of internal energy of internal energy and entropy of our system. Okay.
A working body can be a temperature.
Working body can
has have temperature.
It has temperature. It has temperature. Okay. Okay. Your question is the temperature. Is the temperature a characteristic, or maybe a macroscopic parameter of the working body?
Yes. Okay.
The temperature is a parameter of the working body. The problem here is the following. The working body, it changes, the process of change of its state is cyclic. So no problem. It's time moves and it returns to the initial state.
Maybe average temperature of working body.
Maybe average temperature, but I do not know, but it can be not in equilibrium in each moment of process, maybe, or process of its state. So let us take the engine. If it works with finite velocity, not quasi-statically, we do not have constant temperature, constant pressure, and so on. That's why I do not want to specify the change of the state of the working body at the first time. Then we will talk about the process, but a little bit later. Okay, let us apply. Let us compute the change of entropy of the system. Let us compute the change of entropy. Okay, we know that. Okay. Let us compute. We know that the state of the working body did not change. So its entropy didn't change. So all the change of the entropy comes from here. But for the heat reservoir, we have very simple second law of thermodynamics. The heat reservoir do not interact mechanically. So we have here, or we can and this is Q, and this is Q2. This is Q2. From here, we can modify the right-hand side of equality as follows. TR divided by T1. From here we see that Q delta S2 is Q2 divided by T1. Okay. Q2 is let me. And here I have to put absolute value here. Absolute value because the internal energy increases. And here I will have T2 divided by T1. Q sub 2 minus Q sub 2. And I can present as follows: T2 divided by T1 minus 1 multiplied by Q sub 2. Let me now recall that Q2 is the difference Q1 minus A. And so I have an equality A less than equal T2 divided by T1 minus 1 Q1 minus A. And now I have to distribute all the contributions here, and let me forget about all this. Should we make these transformations? Or I can write out the result. Let me write out the result. I should take A here, and if I collect all from here and here, I will find A is less than or equal than 1, and these guys will change, minus divided T1 divided by T2, and multiplied by Q1. From here, we see that the heat engine efficiency is A divided by Q1. Okay, and A divided, it is less than or equal 1 minus T1 divided by T2. And this is the maximum possible efficiency of heat engine. Let me stress that we start from very general assumptions. We did not specify the type of the working body. We didn't say that it is a gas or maybe something else. We did not say that the change of the working body, the state of the working body changes quasi-statical. We didn't say. It's very general assumption. If our heat engine takes the heat Q sub 1 and the temperature of hot reservoir is T2, this is the efficiency, the maximal efficiency of this heat engine. Okay, we find the limit of the maximum possible efficiency. Let us now address a question. What is the particular cycle that is most effective? Okay, Carlo. Okay, but let us explain us why. For most effective engine, we should have equality here. So this is theta, it should be equal to T1 divided by T2. And this engine should go through a reversible process. Okay, what process is reversible? What process is reversible? It's a difficult question. A simple question asks, what is irreversible? The interaction of two bodies with different temperatures. Okay.
Can we connect the term of reversible or irreversible process with this entropy of the system?
Okay, a reversible process is a process that do not change entropy.
Okay.
An irreversible process is a process in which entropy increases.
Yes.
Okay.
This is simple.
This is simple. But it's important that in reversible process, we can't take two different, we can't allow a contact of two bodies with different temperatures.
Mm-hmm.
So if, it's very, I will take 2 minutes or 3 to explain. Okay, we can consider the contact of two bodies with different temperatures. It's one part of the statement. The second part of the statement concerns working body. If the process is reversible, it is quasi-statical. If it's quasi-statical, this means that state of the working body is in equilibrium.
Mm-hmm.
And now we can say that working body has temperature. Well, only now we can say that body has temperature. Okay, and now we have, well, working body has temperature, let's say T. And to have a process, to make a reversible process, this body should have a temperature T2 when it interacts with hot reservoir, and T1 when it interacts with cold reservoir. So when it has contact with hot reservoir, its state should be changed isothermically. In all the other process, if it has temperature different from this one and this two, but it has, because it can jump the temperature, so it should follow adiabatical process. Its process should be reversible, so the entropy is constant. Mm-hmm. So the entropy is a functional state, and it do not interact to each other. So we apply the well-known formula, delta Q equals T ds. But if delta Q is 0, ds is 0. So this should be constant. All this means that the desired process should be following. Let me draw, and we will make a break after my picture. I write it out in the coordinates, temperature and entropy. So we have the highest temperature of the cycle is T2, and it's the temperature of the hot reservoir. The lowest temperature of the cycle is the isotherm, with the temperature T sub 1, and it's cold reservoir, temperature of the cold reservoir. And here we have idea for X. And let me denote the lowest and highest value of the entropy by S1 and S2. Let me mention that S1, and sub2 and S2 are the parameters of the cycle. So we expect they can be changed without changing efficiency. This means that we have a class of cycles that have one and the same efficiency. Okay, for example, let me continue here. And the cycle should go in bit. It should be, this is the direction of the cycle. Let me write the name Carnot cycle. Let us make a break and we will resume in 5 minutes. Okay. Now we see that now we see that the Carnot cycle is a cycle that have maximal possible efficiency. At C, it's eta maximal, and it's 1 minus T1 divided by T2. Okay, and a possible question is the following. Can we find another cycle that has same efficiency? Can we find another cycle that has same efficiency? So, is the Carnot cycle is unique with such property or not? And here we will prove a theorem. We will say that this is the theorem of Carnot. And he proved it very long time ago, in 1824. And in his original proof, he understood the nature of heat in incorrect way. So he assumes that some substance produce heat. As now we know that it's incorrect. And this theorem says the following. The efficiency of cyclic process, the efficiency of reversible cyclic process with the highest temperature T2 and the lowest temperature T1 is less or equal to the efficiency of the Carnot cycle with these temperatures. So the theorem says the following. If we have another cyclic process, let me draw this in this way. And this process has the lowest temperature T1 and the highest temperature T2. And these temperatures, it's not a good idea. Let me correct. Let me some correction make. Let me another. let me write out this way cycle. Just to have maximal temperature and minimum temperature different from the temperatures of reservoirs. Let me this way cycle. And let me denote this temperature by Q1 asterisk. This one T2. The Carnot theorem tells us that the efficiency of such cycle is less than the efficiency of the cycle, or equal maybe to the efficiency of the Carnot cycle with temperatures T1 ast and T2 ast. The theorem is very important by one simple reason. In real life, a heat engine whose working body goes through a cyclic process has a temperature between the temperature of hot reservoir and between the temperature of cold reservoir. Because we need an infinitesimal time to make temperatures of working body and reservoir equal. So we need to wait a very long time when they will be in thermodynamic equilibrium. And if we want to make a process faster, we should have here a gap in temperature and get the temperature here. And this theorem tells us that the efficiency of such cycle is less than efficiency of the Carnot cycle, whose temperatures, the lowest and highest, equals to the temperatures of reservoirs, but it's even lower than the efficiency of Carnot cycle, whose temperature is equal to the lowest temperature of the cycle and highest temperature of the cycle. Let us prove this theory. Let us consider a Carnot cycle whose temperature is T1 ast and lowest temperature T1 ast and highest temperature is T2 ast. So, okay. I will draw this cycle and this cycle. This goes. Okay, and I will take the minimal value of entropy equals to the minimum entropy of this cycle and maximum value entropy to the maximum value of entropy of this cycle. So I will write Carnot cycle in this way. This does not spoil nothing because the efficiency of Carnot cycle do not depend on the values of entropy S1 and S2. And now let us consider the process that is happening with our body. Let us write points A, B, C, D. When our working body goes from state A to state C, its entropy increases. This means that it gets heat from the hot reservoir.
May I ask a question?
Okay.
The Carnot cycle is a reversible cycle. Is a
Reversible cycle.
Okay. reversible?
It's reversible by two reasons. First, the state of the working body. The process is quasi-statical. It's the first part. The second part, the highest temperature of the cycle equals to the temperature of hot reservoir, and the lowest equals to the temperature of the cold reservoir. That's why when the body follows Carnot cycle, we have interaction of two bodies with infinitesimal difference of temperature. Okay? That's why it's reversible. If I write this cycle, it's not necessarily reversible. Why?
Because the lowest and higher border of temperature may be at different.
Okay, from here to here, entropy increases.
Yes.
This means that it interacts with hot reservoir. The temperature of hot reservoir is T2. It's somewhat here. The temperature of my working body is lower. So we have interaction of two bodies with different temperatures. This process is not reversible. That's why this cycle is not reversible. Okay?
Okay, a part of the difference between temperature go to the work.
What did you say?
We have some value, and this value, the difference between T1 and T2 and new cycle, and the difference between T1 and T2, and difference between cold reservoir and hot reservoir. This difference between these two differences go to the creation to a work, or
no.
go to the cold reservoir.
When we have interaction of two bodies with different temperatures, they just exchange their energy without producing a work. If we have a hot brick and cold brick, I take them and they interact, and I have two bricks. Okay, hot brick gives heat to the hot brick. Gives heat to the cold brick. Okay, it gives out its energy. Its energy decreases.
Yes.
But we have no work.
Okay, I understand.
Okay, and in this process we have less work, because the exchange of temperature goes without producing a work. And this is the problem. Okay, and let us now consider the cycle and consider the maybe arc A, B, C. And the area under the arc A, B, C is the amount of heat that is obtained from what reservoir, because delta Q equals T ds. So Q1, okay, let me put here the point E, and here the point F. Q equals S, A, B, C, D, E. And this is Q1. When the system goes from the state C to the state A, it gives out heat to the cold reservoir. Okay. Okay, I tried, but thank you. So Q2 equals to the A of, C, F, CFE AD. Okay.
ABCDE. First S.
First C, F, E, A, D. This one. And the efficiency?
I say about first S. ABCDE. First S.
First S.
First.
First.
Да. ABC.
ABC. FE. Thank you. Thank you. By definition, efficiency equals to, and here absolute value of Q2. Q1. Q2. And divided by Q1. Okay. And now let us compare these quantities with the quantities of Carnot cycle. In Carnot cycle, okay, and let us denote by Q2C the quantity that is obtained by system in Carnot cycle from hot reservoir and not Q1, okay, Q1, this Q1, okay, it is here Q1, Q2. And here, okay, we should introduce a couple of points. Let me write point A prime, B prime, C prime, and D prime. Okay, Q1 Carnot equals to S A prime, B prime, F E, and here C prime, F E, D prime. And the areas, and we see that these quantities are different by areas. Let us denote. It's not good. I need blue pen. Okay, let us denote the area of these triangles, small triangles, by Q1. And the area of these two triangles by Q2. Okay, and here Q maybe, okay, Q2. And it is clear that Q1 equals to the Q1 Carnot minus Q1. And Q2 equals to Q2 Carnot, and it gives out more energy, so here should be minus Q2. And let us now apply computer efficiency. Q1 minus absolute value of Q2 divided by Q1. Here I put Q1 Carnot minus Q1. Here will be minus Q2 Carnot minus Q2, because this quantity is negative, and in here I will get Q1 Carnot minus Q1. Now I make simplifications. I've seen that Q1 Carnot minus Q2 Carnot is in fact a work. So it's eta Carnot multiplied by Q1. It's first simplification. And now I continue the formula. This eta Carnot multiplied by Q1 Carnot minus Q1 minus absolute value of Q2 divided by Q1 Carnot minus Q2 minus Q1. And now I divide this fraction into three parts. What I do, I add and subtract the quantity and eta Carnot plus Q1. And then I divide this by this. And here I get eta Carnot plus, or maybe minus, it's better to take minus, Q1 divided by Q1 Carnot minus Q1. And here 1 minus eta Carnot and minus Q2 divided by Q1 Carnot minus Q1. What we see? This guy is, okay, let me take this minus sign. This guy is negative. Because this is a positive quantity, this is a positive quantity, this is a positive quantity. Eta Carnot is less than 1. It's important. And here, this guy is also negative because this quantity is positive and this quantity is positive. This means that the efficiency of our cycle is less than efficiency of Carnot cycle. This suggests the following, maybe the following rule. The engines that follow irreversible process are less effective than engines that follow a reversible process. The engines whose working body follows a quasi-statical process, which is different from Carnot cycle, are less effective than the engines that follow a Carnot cycle. Let us now consider an example of computation of efficiency of the engine, and let us now see again that Carnot cycle is most effective. Okay, let us consider example. Let us consider example. Let us assume that the working body is ideal gas. We know that the fundamental relation determines the system, and in this case, it has the form U equals to C multiplied by logarithm S plus R logarithm. Okay, this is a fundamental equation, and it has a consequence that, in fact, the internal energy is proportional to the temperature. Let me, sometimes we write here U sub 0, it's the energy of the gas at 0 temperature. Let me forget about this term. It doesn't interesting here. Okay, and let us now determine a cycle. It includes two adiabates with the values of entropy S1 and S2. But the curves that connect these adiabates are isochors. So, curve connect. And here we go here and here. Go here and here. Okay. And let me label temperatures here T1, here T2, here T3, here T4. So here we have S constant, here we have S constant, and here V equals to V1, V equals V2. Let me read. Okay, let's add here S equals to S1. Go here S equals to S2. Okay. And this is a cycle. Here there is one interesting point. If we have two adiabates, isochors here and isochors here, we can show, and here we have two adiabates, we can show from here that T1, maybe T4 divided by T1 equals to T2, T3 divided by T2 equals gamma. So the ratio of temperatures is one and the same here and one and the same here. This comes from the equation of state. Here I put CVT, and let us here I put CVT. And if I have two states, let me label one state, T1, and I have another state, state 2. I have something like this. That's 2. V2. And if I divide this by this, I find T1 by T2 equals to the ratio entropies. Okay, no. Plus here Okay. Let me. I'm not correct here. Let me believe here. That's okay. So we have, and let us consider the working of this process. This is idea bricks. Okay. Here, our system do not interact with heat reservoirs. So our system interact with heat reservoir only at this stage of the isophores here and isophore here. Here our system gets a quantity of heat Q1, and here it goes out the quantity Q2. On the other hand, this is isochoric processes. This means that the volume of the system do not change. In this case, we can write out delta U equals to Q minus A, but A to 0, so delta U equals to 0, isochore, and Q1 is if I think that it's 0.2, it's 0.1, it's equals U2 minus U1, and Q2 equals, okay, final minus U4 minus U3. Okay. Now, and these quantities can be represented in terms of temperature, because U equals to CV3. So I have here CV multiplied CV multiplied T2 minus T1, and here I get CV multiplied by T4 minus T3. Now, now I can find the efficiency of the process. Q1 minus absolute value of Q2 divided by Q1, U2 minus U1 minus U4 minus plus minus, okay, minus this plus maybe minus U4 plus U3 divided by U2 minus U1, and here I get heat capacity as a common factor, so I have T2 minus T1 minus T4 plus T3. Let's see, heat capacity again, T2 minus T1. I erase heat capacity. I erase heat capacity. And now I see here one minus T3 minus T4 divided by T3 minus T4 divided by T2 minus T1. On the other hand, we agreed that T4 equals to gamma T1 and T3 equals to gamma T2. So we have eta equals gamma T1 T2 minus gamma T1 divided by T2 minus T1, 1 minus gamma. So here we find an efficiency of this process. Let us see that this efficiency is lower than the efficiency of eta kernel. Indeed. Indeed. Eta kernel equals to 1 minus divided by T, let me write T minimum divided by T maximum, where T minimum is the minimum temperature of the cycle, and here, and T max is the maximum temperature of the cycle. In our cycle, maximum temperature should be T1, and lowest temperature is T3. Okay, should be 1 minus. And this is for Carnot cycle with the same maximum temperature, same minimum temperature. And this quantity is higher than the efficiency of the cycle, because gamma is a quantity that we subtract from 1, which is equal. Gamma equals T. I want T3. Oh, no. This nothing here is not correct. Here is not correct. T3 by T1. Gamma equals to T3 divided by T2. And T2 is lower than T1. This means that this gamma is greater than T minimum divided by T maximum. This means that our engine is less effective than the engine that is working a Carnot cycle. That's all for this lecture. Do you have questions? If no questions, we will see next week. Thank you.